Welcome to tonight's Aldehydes and Ketones Reactions and Practice live review session. Today's topic is specifically for students in undergraduate level organic chemistry, learning the ins and outs of these individual reactions, as well as if you're preparing for an exam that has organic chemistry on it, like the MCAT, the PCAT, the DAT, and these reactions will be covered as well. You'll need to know it, but perhaps in different types of detail. So with that, let me know where in the world you're joining from and what you're most excited to cover in tonight's session. While you're typing that in, let's start with the basics. If we are talking about aldehydes and ketones, what is an aldehyde and what is a ketone? So an aldehyde and a ketone are actually very similar in terms of the molecule, in terms of the functional group. The only difference is where it shows up. The key functional group for an aldehyde or a ketone is a carbonyl, a carbon double bound to an oxygen within the chain. And you're going to see this a lot more with your carboxylic acids and derivatives later, but now we don't have anything else with it. An aldehyde has a carbonyl at the end of the chain, for example, this molecule right here. And a ketone has a carbonyl in the middle of the chain, for example, this one right here. So notice they both have that carbonyl. The difference is the carbon, whoops, did not mean to do that. The carbon that has the carbonyl, this one right here, look at what is next to it. The aldehyde has the carbonyl, a hydrogen, and an R group. The ketone has a carbonyl, an R group, and another R group. That's the main difference. And the way I remember it is that a ketone does not want to be alone, and therefore it's in the middle of the molecule. With this in mind, it's not enough to know what they are. You also have to know how to name these molecules. Can you name the structures that I drew? They're very simple, they're very similar, but what is the difference in the name between them? The way to approach naming, I like to use the puzzle piece approach. So let's take it one molecule at a time and break it down. For the first one, I have a 4-carbon chain with an aldehyde at the end. And so we number the chain for the aldehyde getting the lowest number. So that would be 1, 2, 3, 4. A total of 4 carbons for our first name of bute. Only single bonds in the chain, single bonds specifically carbon to carbon for our last name of ane. And that carbonyl on the end being an aldehyde gives me an Al. Because the aldehyde is a terminal functional group, meaning it's always going to be on the end of the molecule, as the highest priority, it's an automatic and understood number 1. So we don't need to put 1 al, it's just al implied to be number 1. Anytime you have a functional group with a vowel following a vowel here, you drop it, you put the name together, and you get butane, drop the E, al for butanal. If we look at the same thing for the ketone, I'll draw it side by side so you can see the difference in how we put it together. Once again, we have a total of 4 carbons, 1, 2, 3, 4. I number so the ketone has the lowest number. We have 4 carbons in the parent for our first name of bute, only single bonds for our last name of ane. But this time, because the ketone technically could show up elsewhere, in this case, it really can't. The only possible ketone on a 4-carbon chain is butanone. And, oh, I just gave it away. But I challenge you to prove that it is correct. The ketone comes on carbon 2, -one. For the suffix is -one for ketone. Now we have 2 ways of putting this together. The first is to bring that 2 out in front of the name and giving me 2-butane, drop the E, -one for 2-butanone, or keeping the 2 where it is for a first name of butane -2-one, butane 2-one. Notice I didn't drop the E this time because I'm following with a number. Let's make sure that's a 2 and not a Z. I follow with a number, but when I have a vowel directly following the vowel, that's when I drop the E. Now, what is it about aldehydes and ketones that makes them so reactive? What is going to drive all the reactivity for this chapter and a lot of the upcoming chapters that you're going to see as well? It has to do with what you see on the carbonyl itself. The carbonyl is drawn like this. Forget what's around it. A carbon double bound to an oxygen. It looks pretty happy. It looks pretty stable. But don't forget, pi bonds are capable of resonance. And a molecule like this can actually have the electrons from the pi bond resonate up onto the oxygen, giving me another not very stable but still significant resonance contributing structure. So now we have the two green lone pairs that we had initially, the red electrons that I just kicked up from the pi bond. And if we look at the charges, I get a minus charge on the oxygen. It's a little bit harder to calculate for carbon, so let's just quickly put in an R on each side. That way, if you want to do a formal charge, you'll realize carbon is deficient. It gets a charge of +1. This right here is not a very stable structure. We have an incomplete octet on carbon. We have a separation of charge. So obviously the major contributing structure will be the neutral form. The minor structure is going to be this mess of an unhappy situation, but together, this is what makes up the carbonyl. And specifically, this is what you have to keep in mind, because reactions don't happen with one or the other. It happens with that resonance hybrid. And that resonance hybrid looks something like this, with the electrons kind of going up and down. Some of the time they're up here for a partial negative. Some of the time they're down here for a neutral pi bond. And the carbon has a partial positive. When you see a carbonyl, therefore, and it looks so innocent and so happy, minding its own business, don't forget partial negative, partial positive. And this right here is the key to understanding, well, everything that's about to happen. So with this in mind, let's take a look at the basic, no pun intended, attack that we're going to see. A lot of the carbonyl reactions in this chapter is, or the initial chapter in aldehydes and ketones, a lot of the reactions will be a direct nucleophilic attack. And the more advanced reactions, which we can cover in another session, is when you have an attack on the nearby carbon. So for a direct nucleophilic attack, we have a carbonyl, which you should remember has a partially positive carbon. Any nucleophile can come in, assuming it is strong enough. And for the sake of this reaction, let's show this as R1 and this is R2. The nucleophile will use its negative or partial negative electrons, attack the carbonyl carbon. At this point, if I form a pi bond to the carbon, it's going to have, well, not a pi bond, I'm sorry. If I form a new bond to the carbonyl carbon, it's going to have a total of 5 bonds, which makes it impossible. 5 bonds exceeds the octet. And so carbon will have to break one of the bonds between itself and oxygen, release it up onto the oxygen atom, giving me a new structure that now looks like this. We still have R1 and R2. We now have the nucleophile also attached, and we have the 2 initial lone pairs. The third lone pair comes from the pi bond that broke and the negative charge on oxygen. At this point, we can have something come in to neutralize it, oxygen attack, different things can happen. But the key behind a lot of the mechanisms that you're going to see is the nucleophile coming to attack like this. A lot of professors will ask you about stereochemistry. And so what you want to recognize is that the carbonyl carbon before the initial attack is sp2 hybridized. What is the shape of an sp2 hybridized carbon? Meaning, what is its geometry? Anything sp2 hybridized is trigonal planar, which is good if your professor tests you on this, but really what you want to know is that it's flat. And if it's flat, it can be attacked from the top or from the bottom. The resulting molecule here, this is typically an intermediate called the TCAI. Most professors don't require you to know it, but it's a tetrahedral carbonyl addition intermediate. This is sp3 hybridized, this carbon right here. And that means if chiral, it will be racemic because you could have had some of the attacks happen from the top, some of the attacks happen from the bottom. So you're going to get a mix of R and S. So we have a general idea of where the chapter is going, what type of reactions we're going to form. But the first thing your professor is going to ask is how do you make an aldehyde or a ketone? Assuming you're covering this topic early organic chemistry 2, you're going to have to remember a couple of reactions that you learned in organic chemistry 1. The first one will be the alkyne hydration. If you forgot this reaction, make sure you check out my alkyne videos because I cover them in detail. We'll do a quick summary here. And I'm specifically going to use one molecule to show you 2 different reactions. If I have a terminal alkyne, notice that I have a hydrogen on the end. That means I have a carbon here with only 1 carbon attached, and this one has 2 carbons, the internal and the terminal. This is really important because depending on what I use, I can get a total of 2 different products, which is going to be very helpful if I want to control the aldehyde or the ketone forming. I'm going to show you the products, and I want you to think of what it will take to get that product, meaning what the reagents have to be in each case. For the first one, I want to form a ketone. That is a carbonyl on the internal, on the second carbon. For the second one, I want to form an aldehyde. That is the carbonyl on the primary or terminal carbon. The difference between them is very specific in terms of the reagent that you use is going to control where the reaction happens. For the first one, to get the ketone, I have to use an oxymercuration reaction. For oxymercuration, in this case, we'll use HgSO4 in the presence of H2SO4 as the acid catalyst and some water. H2SO4 is an aqueous acid. The product in this case is actually not going to be a ketone. What this is going to give me, very similar to what I had in an alkene reaction, only 1 pi bond breaks to give me an alcohol. This is very similar to the alkene alcohol formation. 1 pi bond breaks, the second one is still there. I have an alcohol forming on the more substituted carbon, just like the alkene that follows Markovnikov's rule. And then, and this is going to happen automatically, is a tautomerization reaction. KET stands for keto-enol tautomerization. Because what I have here is an alkene and an alcohol sitting on the same carbon. This carbon right here has an alkene and an alcohol together, or simply called an enol. Enols are not very stable, and they will tautomerize. I have a mechanism video on this if you want to see in detail, but ultimately what happens is this hydrogen comes off, you form a pi bond here from this pi bond having moved, and then you just replace a hydrogen there, giving you this right here and an extra hydrogen on the side, which we'll just assume is there based on skeletal structure. Keto-enol tautomerization can happen in acid or in base. And in this case, because I'm already in acidic conditions, I don't have to show anything. I don't have to add any reagents. In fact, I cannot isolate the enol because it will automatically just go straight forward all the way through. For the second one, if I want to get it terminal, I'm going to use a form of hydroboration. For alkynes, you tend not to see BH3. So for example, B2H6 is just another form of hydroboration. It's 2 BH3s put together. And then you'll see NaOH, H2O2. That's step 1, that's step 2. And this is typically enough for what your professors want to see. Once again, just like the first reaction, oxymercuration, you're going to get only 1 pi bond breaks. That means the second one is still there. We get an alcohol at the primary position because this is an anti-Markovnikov reaction. This, once again, is an enol because this carbon has an alkene and an alcohol, not a very stable intermediate. And the enol will automatically undergo keto-enol tautomerization, except this is technically not a ketone keto-enol because it's an aldehyde, but the concept of keto-enol applies. You get an aldehyde at the terminal carbon, and that is the same setup, but because we used an asymmetrical molecule, we were able to control it for two different products. If you're with me so far, go ahead and give me a heart in the chat. And then I want you to let me know in the comments which other reactions you learned in Orga 1 that could give you an aldehyde or a ketone. The next reaction that you should remember is ozonolysis. Ozonolysis has ozone in the name, and that is your clue for what's about to happen. With ozonolysis, the mechanism is very, very tedious, so for your sake, I hope you don't need to know it. What you should know is what happens. If I react an alkene with ozone, O3, that's step 1. Step 2, DMS, not DMSO, that's a solvent you'll see in SN2 reactions, DMS, just the S, and a lot of students do confuse it. This is an oxidative cleavage reaction where the trick is very simple. All you do is slice the molecule through the pi bond, put an oxygen on each piece that you just cut off, and draw it exactly as you see it. So if you have something like this, that's the first half, the second half, put your oxygen in, and look at that. If the alkene, the carbon on the alkene has 3 carbons attached to it, so notice that this one has 1, 2, and 3, it's more substituted. It's going to give me a ketone. If it only has 1 and 2 attached to it, it'll give me an aldehyde. Now, students have often told me they get confused here because I'm drawing an arrow to a carbon that's about to get cut off. So think of it this way instead. If the carbon holding the pi bond has an additional 2, that's a ketone because ketone has 2 bonds to carbon. If it has just 1, that's an aldehyde. And so my products here are ketone and aldehyde. In this case, I did get 2 products, but there are situations where you'll get just 1, and professors love doing this to you in synthesis. So for example, I'm giving you the reactant, but they like to start this one with a product. You have something like this, react it with O3, followed by DMS, and look at that. Even though we cut it in half, and even though we get an aldehyde and a ketone, we only get 1 product. I can number the chain like this, 1, 2, 3, 4, 5, 6, 7. I find it easier to number rather than trying to copy. And then I just draw it out like this, 1, 2, 3, 4, 5, 6, 7. And see what you have on the carbons that you broke. Carbon 1 gets a carbonyl. I don't even have to think if it's an aldehyde or a ketone. Do you realize how I'm letting the trick guide my product rather than having to think about it? Because carbon number 1 is terminal, I know it's an aldehyde. I don't have to worry about it. Since carbon 6 gets a carbonyl, let me move the 6 so we can see it, and it happens to be internal, then it's a ketone. I don't have to worry about it. I don't have to think about it. It just appeared as a ketone using this trick. All right. If you have any questions on this, go ahead and type it in. The next reaction that you should, or that many students will have learned already, but not everyone, is oxidation. And we actually covered oxidation of alcohols in the alcohol live stream. So make sure you watch that next if you're not comfortable with this. But let's do a quick review. If I have a primary alcohol, for example, something like this, and I oxidize it using a strong oxidizing agent like a chromic acid or some version of it like sodium dichromate, the alcohol can get oxidized twice, so double oxidation. The first is to an aldehyde, and the second is to a carboxylic acid. Now, for the sake of the chapter on aldehydes and ketones, we don't care about the carboxylic acid. We want to stop at the aldehyde. The thing is, every strong oxidizing reagent will take the reaction all the way through to a carboxylic acid. It will not stop. And so if you want to stop, you have to specifically use a weak oxidizing agent, PCC. This one is going to stop at the aldehyde. And a mnemonic I got from one of my students is because PCC starts with a P, you remember it's a prude. It doesn't go all the way. It stops at the aldehyde. If, on the other hand, you start with a secondary alcohol, the secondary alcohol only gets oxidized once without breaking the chain. And so it doesn't matter which oxidizing reagent you use because it goes from a secondary alcohol to a ketone. So primary, secondary, and that's how you get your ketone. That's how you get your aldehyde. And of course, this one will keep going to a carboxylic acid. So let me know in the comments, even if you're watching the recording, if you covered oxidation in Organic Chemistry 1 or if it's something your professor is teaching you in Organic Chemistry 2. Now, on your exams, you're not going to see the reactions this pretty, this simple. Your professors are going to make it nice and interesting. For example, using this right here as your starting molecule, show me what you're going to get when you react it with Na2Cr2O7, something like that. The ring here is meant to scare you. Let me know in the comments if when you see a ring, your mind just goes, oh, scary. Don't let the ring scare you. Take a look at this. Doesn't it just look like a sideways chain? All I want you to pay attention to is the piece that you need to know. And the piece that we need to know is the carbon holding an alcohol. That's going to get oxidized. Secondary alcohol, the most you can oxidize is to a ketone, and boom, there's your product, exactly as we saw before. Question, does PCC only work for aldehydes or just in that case? No, it's not that PCC only works for aldehydes. Let's go back. PCC is a reduced capacity oxidizing agent, means it's not very strong. And so after the aldehyde, it does not have the strength to keep going and form a carboxylic acid. But I can also use PCC over here because to get a ketone takes about the same strength of oxidation as I need to go from an alcohol to an aldehyde, because all I'm creating is one carbonyl, one extra bond. And so in this case, PCC will work just as well. So I'll put a note here, or PCC, and you'll get the same product. Madeline, that was a very good question. I don't want you to think it limits, but it's one that will work for a secondary, but we specifically want to use it for primary if we don't want to go to the carboxylic acid. Great question. All right, so we have the basics. We know how to create our carbonyls. Now let's go back to the reactions. We already talked about the fact that the carbonyl reactivity has to do with the partially positive carbon, the partially negative oxygen, and the fact that a nucleophile is going to feel very welcome attacking that carbonyl. So how does that actually play out in different reactions? Let's drag that down. And let's start talking about specifics with these reactions. The simplest one we can talk about is hydration. If I have a ketone or an aldehyde, it'll work the same way. And I bring this into a situation of, let's go with a base like NaOH. Anytime you see NaOH, recognize that you have a positive spectator. Get rid of it. OH minus, that is the nucleophile. That is the reactive species in question. That OH minus, just like I showed you with a nucleophile, attacks at the carbonyl carbon, creating a new bond, too many bonds, and ultimately kicking out the pi bond. After kicking out the pi bond, I'm left with an O minus. That's because the oxygen now has the extra lone pair of electrons from the pi bond, and then a new bond between that central carbon and the OH that just came in. This right here, in the presence of a base, is no problem. I'll probably have water or something similar as the solution, but a base that allows an OH minus to exist is a base that will also allow an O minus to exist. Base allows a base to form. Be very, very careful because we're going to contrast it shortly. The base allows the base to form. This is technically my end of the mechanism, but I can't leave a molecule hanging with a negative charge. And so in the next step, we're going to protonate as follows. Just grab a proton off of water, and that'll give me something that looks mostly like what we had, except that lone pair is gone, and I now have another hydrogen. So this right here is called a diol. Specifically, it's a geminal diol. It's like a gem. You hold two in the same hand because you don't want to let it go. And the diol is not very stable. So you're typically not going to see it exist as is, but you should know how to do the reaction. This is a base catalyzed reaction. I can also do hydration as an acid catalyzed reaction. This is where a lot of students get confused, so make sure you pay close attention. If I try to carry out this reaction in acidic conditions would be some kind of acid catalyst like H2SO4, giving me H plus in solution, dissolved in a solution of water. What is my nucleophile in this case? In the basic solution, it was very obvious. I have OH minus. OH has a negative charge, therefore it does the attack. If I have an acidic solution, this is where you want to pay very close attention. An acidic solution will not, do not lose points on this, too many students do, will not allow an O minus to form. Never, ever, ever show me an O minus in an acidic solution. An acidic solution is a positive solution. Therefore, the most negative thing in a positive solution is what? What is my nucleophile here? It's water. Water has the two lone pairs. That is very reactive in this situation. But if I attack and kick up these electrons, that forms an O minus. And I absolutely cannot form an O minus. So I have to come up with something else. Instead of forming an O minus and figuring out what to do with it, let's just never form an O minus by activating. So that's the key. Acidic solution will have to have an activation step first. The way that you activate is oxygen on the carbonyl grabs the H+. That is going to give you a protonated carbonyl, only one lone pair, a new bond to the hydrogen with a positive charge. Now that oxygen has a positive charge, it was greedy. It reached out for that proton, and now it has regret. It doesn't want to be positive, so it starts pulling on the electron density between itself and carbon, making carbon even more partially positive and even more susceptible to attack. That is where this reaction takes place, or where the reaction can actually begin, because now the water is even more likely to attack when the carbon is even more partially positive. Now, if I kick up the electrons, I don't form a negative charge, I get a neutral oxygen. Look at that. Oxygen had the purple lone pair. It has the green hydrogen, and now it gets what we'll show as the blue lone pair. It's neutral. Attached over here, I have the green water that just came in. Let me draw this a little bit differently so we can follow the pieces. We'll draw it like that. And then this right here has a lone pair, positive charge. We don't want to leave our product with a charge, so the final step is going to be deprotonation. In base, we protonated. In acid, we deprotonate. We'll use another water molecule in solution to grab the proton, give oxygen back the electrons, and that gives me a final neutral product, same as what we saw for the base catalyzed reaction. We just went about it in a different way. Once again, I have a diol. I went through the detailed step-by-step mechanism here, but I am going to challenge you to see how the next mechanism I show you is pretty much exactly the same thing that I have here. Are you ready to see how the acetal mechanism is exactly the same? If yes, give me a heart. Let me know in the comments. All right, I see the hearts coming in. An acetal is a molecule that has two OR groups. So an acetal looks like this with an OR and an OR. Well, technically, that's not an acetal. Technically, it's this. So let me show you a couple of different molecules and explain why your professors are confusing you by accident and not on purpose. If I have an aldehyde and I react it with an alcohol in the exact same reaction that I just used above, but instead of water, I use an alcohol, the molecule that I get is going to look like this. I will have an O and an H, and then here I will have an OR, and that's a hydrogen, like that. This is a half acetal, and so it's a hemiacetal. If I react this one more time in the same reaction, that OH is going to get replaced. Let's show it in a different color so you can follow where everything came from. That is going to get replaced with, well, we already had a green OR. Now we have a purple OR. This right here is called a full acetal or simply an acetal. But if I take this entire reaction, and for the sake of, I don't want to rewrite this, so let's just do that. If I start with a ketone instead, so here I have an aldehyde, and here I have a ketone. The only difference is that this chain is a little bit longer. Whoops. This chain is a little bit longer. A ketone won't give me an acetal, it'll give me a ketal. Aldehyde, acetal. Ketone, ketal. And then same thing here again, extended chain because it's an R group, and I will get a ketal. Now that you know the difference, be prepared to have your professor call both of them acetals. And the way that I like to think of it is simple. If we are talking about different types of creatures, we are talking about canine, dogs, feline, cats, man, humans. When I compare a canine to a feline to man, I'm not talking about a male human. I'm talking about a human in general. And when I say this represents man, it could be a man or a woman. That's more like the big category. And so when you're talking acetal, it's like saying the category of man, which includes male and female. The category of acetal includes acetal and ketal. Long-winded explanation for why your professors are going to call both of them acetals. Now that we get it, let's take a look at the mechanism. You can get the hemiacetal in base or acid, but you can only get the full acetal in acid, not base. So let's go through the mechanism quickly. And I want you to recognize how this is exactly like the previous mechanism. And so many of your future mechanisms are going to be exactly the same. We start with a protonation step. Oh, by the way, this is a fully reversible reaction, so everything can go backwards and forward. We start with a protonation step. Well, oxygen grabs the proton, and that gives me an activated molecule, one lone pair, positive charge. The next step in the hydration, water attack, and so in this case, we'll have alcohol attack. We'll show it as a CH3OH. Oxygen, just like in water, comes into attack to kick out the electrons. Again, reversible reaction. This will give me a molecule that now has the O, the H, and then the CH3OH. In the previous one, we showed the next step, again, reversible. We showed the next step as the extra proton getting removed, a deprotonation reaction. So we'll show another methanol in solution coming in to grab the hydrogen. It's not that, it's the oxygen. Grabbing the hydrogen, giving the electrons back, and that will give me my intermediate, which is my hemiacetal, which now has this OH and this OR, OCH3. This is neutral, but the reaction is technically not done because this can keep going in the presence of additional acid. One of the oxygens is going to grab another proton from solution. Now, this is where you want to be careful because a lot of students will ask me, Leah, how do you know which one is going to grab it? Very simple. We don't because they both do. Well, how do we get a product if they both do? Let me show you. If it happens to be the CH3, the OCH3 that grabs a proton, well, we're just going to get that. And did I not say it's a reversible reaction? So it'll go this way and that way and this way and that way until eventually we get the product. So we're not going to show the OCH3 grabbing it because we don't want to go backwards. We already know that it can. Instead, we're going to show what happens if the reaction goes forward because the OH grabs it. This is going to give me, I do not want to redraw this a million times, so we're just going to do that. This is going to give me this lone pair having disappeared, and apparently the oxygen too. Attached, I now have the red hydrogen, only one lone pair and a positive charge. Water in this case is a good leaving group, but it's not necessarily going to leave on its own. It needs a little bit of a kick. And that comes from the OCH3 being greedy and saying, oh, if you're trying to leave and pulling on the electron density, making that carbon partially positive, well, I'm going to give you a hand, kick you out. And when the electrons come down from the OCH3, water as a good and stable leaving group gets kicked out. And that gives me, well, look at that. I have a funky looking, almost like a ketone with a substituent. But this is my intermediate. This was the OR group now having a carbonyl. And the carbonyl, just like in the starting carbonyl, is very partially positive and susceptible to attack. Another alcohol in solution will do the same exact thing as we just had. Attack the carbonyl, kick up the electrons. These are all reversible. There we go. Kick up the electrons, and let's just show this being reversible. Okay, so we have hydrogen. Are you guys with me? I know that I'm going through this very quickly, but I hope that you're still following or able to follow. And of course, you can pause the video. That's the beauty of YouTube. Even if I'm teaching live, you can still pause the video and make sure it makes sense. Now I have an H, a CH3, lone pair, positive charge. And so we bring another alcohol in solution to deprotonate. And boom. That brings me to my final product, which looks like this. We no longer have to show this hydrogen because we don't show that in line structure. It's no longer on an aldehyde. I have an OCH3 here and an OCH3 here. And again, reversible. Okay, that seemed like a whole lot of to do, but what is the point of an acetal? Why do we even need it? Do you know? There are a lot of reactions that will attack a carbonyl. as we're actively seeing. But let's say you have a molecule where you don't want your carbonyl attacked. The way that we have a carbonyl being reactive, what if that carbonyl could be turned into something like this, not reactive? Reactive, not reactive. So the acetal is a really good way to temporarily render that functional group not reactive so that you can carry out whatever other reaction you had in mind. For example, if I have something that looks like this with a carbonyl here, and say I have an ester, and I want to attack the ester, but I want to make sure the carbonyl is not attacked, I'm going to turn this into an acetal. I'll give it a gas mask, a protecting group. Why am I saying gas mask? Very simple. One of the common protecting groups that you're going to see looks like this. If I have an OR, an alcohol, then it would be, say, CH3, or it would be an alcohol with an R group, and then an R group with an alcohol. Well, what if they happen to be attached to each other? And what if the chain happened to be not that long? So it doesn't have to be two separate alcohols. You can have the same molecule that just happens to have two alcohols on it. And this is the one you're typically going to see. Propylene glycol is a very common protecting group in acid. And here's the trick for it. Anytime you have to react to form an acetal, for example this, all you do is redraw the carbon skeleton, in this case, just 3 carbons, cut your oxygen off, and the carbon holding the oxygen, just put 2 new bonds. And so I'll put 2 new bonds, cut the hydrogen off the oxygens, and put it right there. This is why I call it a gas mask, because look how happy it is to be protected from whatever reactions are going on. For the students just joining us, there was a confusion in the setup, and so if you thought the workshop is starting now, it actually started almost an hour ago, but because of technical difficulties, it didn't start an hour ago, and therefore you still have quite a few minutes and a couple of reactions to go. I apologize for the confusion, and you will be able to catch anything that you missed. All you have to do is sign up here. You'll get information regarding the link after it's posted, the worksheet, and session notes. The worksheet will give you even more practice on everything that we covered today. All right, so let's continue. Now that we know how to do the acetals and the shortcuts, let's look at another one of my favorite reactions. Let me know in the comments if you have already covered the Grignard. Spelled with a GN, not an NY, Grignard reaction, pronounced with a Y, spelled with a G. The Grignard is very interesting because it's one of the few times you're going to see a carbon act like a carbanion. It's a carbanion-like reaction, a very strong, nearly negative carbon. A Grignard looks something like this. An R group bound to magnesium and a halogen, for example, bromine. This bond right here between the carbon and the metal is the kind of bond where the electrons almost sit as if they're on the carbon, and that makes this one act like a carbanion. Carbanions, as you should recognize or remember from the beginning of organic chemistry, are very unstable, very reactive, because they're very, very unhappy, and the Grignard is very, very, very reactive. The Grignard is looking for anything positive or partially positive. And so if you think about how our carbonyl reacted earlier, the Grignard is going to do the same exact thing. If I have a CH3 with an MgBr on it, The carbon is going to attack at the carbonyl the same way that the nucleophile attacked before, kick up the electrons, and that will give me an O-, the CH3, and the MGBr is just wandering off somewhere in solution. So this is a very, very important reaction to know, because this is your best bet for chain elongation in organic chemistry too. Your absolute first thing to come to mind when you see that the reaction results in a larger carbon chain, think of a Grignard. In this case, I used a small molecule, but I'll show you an example where it gets even bigger. Now, obviously, we don't want to leave the product with an O-, and so the next step is going to be just a mild acid, something to protonate for the oxygen to grab a hydrogen. That becomes an OH, and here I have my CH3. So let's look at a bigger reaction so you can see how to put this into practice, and then I'll show you a fun trick for this. Say I have something that looks like this with an aldehyde, and I react it with an isopropyl Grignard, like that. The mechanism, first, let's do it the slow way, is the carbon that is attached to the magnesium, that is the carbon that does the attack at the carbonyl position, kicking up those electrons. No, why I said protons. And giving me my near final product, which looks like this with an O-. The extra lone pair from the pi bond gives it the negative charge. But then here's the new bond where the Grignard attacked, and we have that propyl group. So do you see how my carbon chain went from what I had on the green molecule to something that is now so much longer because of the Grignard having added? And the next step is just a protonation. H+ is going to turn this into an alcohol. If you're comfortable with the mechanism, I know I did it quickly, but I showed you two different ones. If the mechanism makes sense, when you're doing this in synthesis, you don't have time for the mechanism. You don't have time to think through it. Michael says, favorite reaction so far? Mine too. It is one of my favorite reactions. So what I want you to recognize is where and how that Grignard comes from, and therefore how you're going to recognize it. In this case, we're dealing with an aldehyde and a ketone, so I'll show you both. If I have an aldehyde and if I have a ketone, reacting it with a Grignard, actually, why am I doing this in red? I want the trick to stand out in red. If I react this with a Grignard, RMgX and RMgX, I'm showing it to you together because the trick is exactly the same. All you do is break the pi bond, turn the O into an alcohol, and then add your R group to that carbon. Let's add it on the other side so that it's easier to see the chain growing. It's the same thing. It's really just a technicality to have it on the other side. And so look at that. You don't have to go through the whole process. It's just the OH. In the case of the aldehyde, this is it. This is your carbon chain. In the case of a ketone, your carbon chain is a little bit more branched, so it's a bit trickier, but you get the same exact thing. What do you think of this shortcut? Did you just save a couple of seconds, if not a minute, on your next quiz or exam? Question, do we also show the MGBR getting kicked off? So that is a very good question. I typically don't. This is not a situation where you attack and then this breaks off. You just show carbon basically steals the electrons so it can go do whatever. I'm trying to think of an example. Say you and your friend are walking, you're walking down the street, both holding on to the leash of a puppy. One of you just got a puppy, you're so excited, you're walking together, and then you see something that for whatever reason makes you want to run. I don't know, the ice cream truck showed up. Love ice cream. So even though you're holding on to your friend, even though you and your friend are both holding the dog leash, you're so excited for the ice cream, you just yank the leash out of her hand and you and the puppy run to the ice cream truck. That's kind of what's happening. So it's not like this is getting kicked off. It's the electrons getting yanked out of its hands. Okay, so let's go through this quickly one more time. We are going to, actually, let's do it with a molecule. Let's make it look, a little bit more scary. So professors love to do big examples with rings and other things going on. So let's do the same thing. Say you have something like this, and you are told to react it with something like this. Okay. Does this look like the kind of problem you might see on your exam? If yes, let's see. We identify that we have a Grignard reaction with a carbonyl. We know it's going to attack at the carbonyl position. Identify that carbonyl carbon, break the pi bond, add a hydrogen there, and then add the R group here. So we're not going to do it on here. We're going to redraw the skeleton. Start by redrawing the skeleton exactly as you see it, up until the carbonyl, which you only draw as an alcohol. You have a new bond, and that is 1, 2, 3 carbons. 1, 2, 3 carbons, and that is your final product. Yes, professors love to use rings to trick you, but did you notice how nothing changed? The ring, whoops, that color is not making it disappear. The ring did nothing for the reaction. Now here is another trick, because you're not always going to have a forward reaction. You're going to have a synthesis problem that says somehow, some way, this right here came from an aldehyde or an alkane, a carbonyl, right? So you're looking at this, you're working on your synthesis, you're working backwards. Here's how to undo this trick without having to take too much time. Identify your alcohol. Boom, found it. The carbon holding the alcohol used to be a carbonyl, and then, depending on your synthesis, either that was added or that was added. And I could show you a situation where both were added. So this could have come from two different types of Grignard reactions. Let's first show what happens if I broke it this way. That means this was my carbonyl and this was the Grignard that attacked. This came from a molecule that looked like this. That's my aldehyde. That's this portion of the molecule. And this was my Grignard, which is just a CH3 MgCl, another version of the Grignard. If, on the other hand, I choose to break it this way, then what I'm looking at is this right here was my carbonyl. That means I have an aldehyde. And this right here was the Grignard that attacked. And in this case, that's an ethyl MgCl, Br, or I, whichever. So absolutely try this, because it's going to save you so much time. Now, this situation, we got an aldehyde in both cases. How did we know it was an aldehyde? Because the product is a secondary alcohol from a Grignard came from the aldehyde. If I had a ketone with a Grignard, that would have had to be tertiary. So take a look at what happens. If I have a molecule that looks like this, okay, this is much more likely something your professor is going to show you. This right here from a Grignard. Same trick applies. Identify the carbon holding the alcohol. That was a carbonyl. Cross out your hydrogen. And then any of the carbons on there could have been the Grignard. So for fun, let's make this longer, like that. If this right here was the Grignard, then very simply, this came from a molecule that looked like this. We have the big ring. And then 1, 2, 3, 4 carbons on it. 1, 2, 3, 4. This right here was my ketone. And then the thing that added was this right here, CH3 MgBr. That's one option. Or I can do it the other way. So I want to show you how both of them could have been an option. This could have also been the thing that attacked. that would have been the starting molecule with just the 2 carbons on it. Still a ketone though. In each case, it's still a ketone. But this time, my Grignard has 1, 2, 3 carbons on it. And that would have been a propyl Grignard. And that is what I got. Oh, I meant to draw the other one here. I don't know why I didn't. Whatever. You can still clearly see what's going on. Wait, there's one more option. I could have also had this. Actually, there's more than one more. There are a lot of options. That could have been my Grignard. Oh my goodness. Okay, so let me show you, since I, by mistake, opened this rabbit hole. I have 1, 2, 3, 4, 5. I could have had a starting molecule that looked like this. 1, 2, 3, 4, 5 with a carbonyl. Let me draw it that way instead. Could have done that ketone. And then the attacker was this right here. MGBR. Okay, so I could have had this attack the long chain. That chain, that chain. Actually, no, it's just 3. I don't know why I was thinking there could have been a 4th one. So these are your 3 different options that each could have led to the final product. Tyler, I don't understand your question. How can we tell if alkylation did not happen but the Grignard did? If the Grignard reaction happens, then it brings a CH3 or a propyl or whatever with it. And so if a Grignard reaction happens, it will add a carbon to the chain. The only time the Grignard will not happen is if you by mistake dissolve it in the wrong solvent. Let's say I have a reaction that looks like this, and I don't realize that my CH3Mg, in this case Cl, needs to be dissolved in ether, and instead I put it in H2O. The Grignard, being very reactive, is not going to attack the aldehyde. The Grignard is going to attack the water, and that'll destroy the Grignard. So the key here is a polar protic solvent. This is a term you should remember from your SN2 reactions. A polar protic solvent destroys the Grignard and cannot be used. Each of the reactions above have to be in an inert solvent. For example, ET2O, THF, I don't know why I put a 2 there, THF, or just ether in general. THF is a cyclic ether. That is going to prevent the Grignard from attacking the solvent molecule and therefore not allowing a reaction to happen. So going back to Sandlish, thank you for reminding me. So the trick here to recognize is the secondary alcohol was talking about this one right here. But the trick to recognize here is that if you have a tertiary alcohol from a Grignard, it had to have come from a ketone. So the ketone gives you a tertiary alcohol, and the aldehyde gives you a secondary alcohol. So these were great questions. Let me know in the comments if you have any more on this. All right, quite a few more. Let's see how many we have time for, because technically we're over time. Let's take a look at reduction. Another reaction that you have to know, and I'm not going to go through the mechanisms individually because I cover this in my redox series, which I'll link in the description. But I want you to understand the basics of reduction. Earlier, we talked about the fact that a primary alcohol is going to give me an aldehyde. I don't know why I'm drawing a carboxylic acid. It would give me carboxylic acid. I'm going to use PCC here because I only want to focus on the aldehyde. And the secondary alcohol would give me a ketone. It could be PCC. It could be anything else. I'm just going to put oxidizing. If I want to reverse the reaction, then I just use a reducing reagent. So reduction is going to reverse it. So an aldehyde will give me a primary alcohol, and a ketone is going to give me a secondary alcohol. Now, a lot of students mix up the reducing reagents. And so I want you to look at what happens with reduction. And I'll just pull one of these. If I have an aldehyde and I want to turn it into an alcohol, if I want to reduce it, what has to happen here, I have to break the pi bond between the carbon and the oxygen. Then I have to add a hydrogen to get an alcohol. And since I'm losing a bond on carbon, I also have to add a hydrogen here. So the net number of hydrogens increases with reduction. So here we already had the one hydrogen, but now we're adding a second one here, and we're adding here. There are a lot of different mnemonics that students use for redox. I personally like Leo the Lion says, grrr. That was my really scary word. Because this tells me that the loss of electrons is oxidation, and the gain of electrons is reduction. Now, what does the loss and gain of electrons have to do with redox in the case of these reactions here? Remember that if you have a proton plus an electron together, that is a hydrogen atom. Hydrogen is just a proton and electron. So anytime you gain electrons, you're also gaining hydrogen. That is reduction. Notice that I gained 2 hydrogen, and therefore I know it's reduction. The reason I'm pointing this out is if you're trying to think about what are your reducing agents, ask yourself, which reagents do I know that have all the hydrogens? The common ones that you're going to learn for aldehydes and ketones, lithium, aluminum hydride. Notice that it has a whopping total of 4 hydrogens. And it's not just hydrogens, they're hydrides. That's the key. What's the difference between a hydride and a hydrogen? And while you're thinking about that, the next one is sodium borohydride, NaBH4. Once again, we have 4 hydrogens. The hydride is a negative hydrogen, and that means we're looking at a hydrogen atom with a lone pair and a negative charge. That lone pair, that's very reactive, and that is where the mechanism comes from. We're not going to go into the mechanism in detail. I just want to show you how it starts so you understand how the hydrogen gets attached. Boom, there you go. The hydrogen, the hydride attacks, and then the rest of the mechanism puts another hydrogen on the oxygen. Lots of hydrogen, lots of hydrogen. You have another one that is an itty bitty one. NaH is just sodium hydride. It's 1 hydrogen, or 1 hydride like that. But it's going to carry out the same exact reaction in that the H- attacks the carbonyl, breaks that pi bond. There are more reactions that you will learn for reduction, especially with a ketone. So if you have a complicated molecule, professors love using rings. So let's go ahead and do this one with a ring. Say I have a ketone. I showed you how sodium borohydride and lithium aluminum hydride are going to turn the ketone into an alcohol. But what if I don't want to turn it into an alcohol? What if instead I want to take this molecule and completely and totally get rid of that carbonyl? Gone. In its place, hydrogens. I have 2 options. In my redox series, I cover them in detail for the mechanism. But the key difference, because depending on the situation, you'll want to consider your acidic reaction or your basic reaction. Pay attention to what's going on so you know which one to use. In acidic conditions, we want to do the Clemmensen reduction. This is ZnHg, so zinc mercury with HCl. That's acidic. The basic condition is a Wolff-Kishner reaction, and that is H2n and H2. This is hydrazine and KOH, which is your base. So this is Clemmensen, and this is Wolff-Kishner. You'll see this a lot in your aromaticity chapter. If you've already done aromatic reactions, let me know in the comments. You'll probably have seen Friedel-Crafts acylation, and then you just cut it off. That's one way to control your reaction, because if you think about it, Friedel-Crafts alkylation will lead to polyalkylation, but acylation is going to reduce the reactivity of the ring, slow it down, then you just cut it off. So fun fact, if you've done that chapter already and you want to keep it in mind for synthesis. John, I am taken, but you are welcome to watch my videos and hear my voice. How do we know if it's acidic or basic conditions? Whatever reaction you have done, so let's say you did a Friedel-Crafts alkylation, look at the reaction and ask yourself, do I have a ton of acid sitting in solution or a ton of base? And based on that, no pun intended there, based on that, you'll know what to do. Now, I mentioned synthesis, so what about, and we have so many different reactions we can still cover, but let's jump over to, say you're told to take this molecule right here and turn it into this molecule right here. Hold on. Let me make sure I have the right one. There we go. Okay. This is your synthesis. This is what you have to do. Somehow, some way, where do you even begin in a reaction like this? The first step in any synthesis, as you'll know if you watch my synthesis session, is not to start thinking of reactions. Instead, you want to ask two simple questions. One, what is the same? And two, what is different? What is the same? We have 4 carbons and 4 carbons. What is different is we seem to have added 2 carbons. What else is different is that we have a carbonyl on carbon 4, and we've somehow moved it over to get an alcohol on carbon 2. How do I even begin to do that? Whenever you see something like that, ask yourself, did I really move it over, or can I maybe do something like this? 1, 2, 3, 4. 1, 2, 3, 4, 5, and 6. Aha, plus 2 carbons. Now, what reaction should have taken place if I turned an aldehyde into an alcohol and also added 2 carbons? You should recognize the trick that I showed you, and that is very simple. Turn your alcohol into a carbonyl, get rid of the hydrogen. Whatever is new got added as your Grignard. That's a one-step transformation, isn't it? Ethyl, Grignard, step 1. Step 2, a source of H+, and that's it. What do you think? Was this easier than you expected when you first saw the reaction? All right, so let's then do another one. Let's see, let's make this a little bit more complex. Say you have a molecule that looks like this, and somehow, some way, you have to turn it into a molecule that looks like this. You know what, let's do this. Okay. What do you think? Easy, medium, or difficult? And how would you approach it? I love this. When a student tells me that a reaction pretending to be difficult is now doable, that means you're learning. That means you're understanding. And that makes this session, with all the technical hiccups in the beginning, totally worth it. So let's see if we can do this for the next one. The first thing we do for a problem like this is we ask the two questions. Question number 1, what is the same? And question number 2, what is different? What is the same is this portion of the molecule. So I always like to identify my carbons, number the chain if you can, but here I'm coloring it up. And then what is different seems to be that all I added was a 2-carbon chain onto the end of an alkene. So I'm adding plus 2 carbons, but the functional group is the same. Do you know of a reaction, especially related to this chapter or any chapter, that will take a molecule with an alkene and simply just glue something onto the end? If you're thinking no, I'm thinking I agree with you. There are some advanced reactions that a lot of students don't even learn that have to do with this kind of adding stuff to an alkene, but let's stick to something that everyone knows. And that trick that I want you to walk away from here is this. If your functional group doesn't seem to work out, then maybe it's not the same functional group. Maybe what I'm starting with is a red pi bond and ending with a blue pi bond that have absolutely nothing to do with each other. And if that's the case, ignore your starting molecule for a moment and ask yourself, if I have a reaction that grows my chain, what kind of functional group could help me grow my chain? And how does that translate into having an alkene there? In Organic Chemistry 1, we grow chains with alkynes, an acetylide type mechanism with a triple bond. In Organic Chemistry 2, my go-to will be Grignards, although a Wittig could have kind of sort of maybe worked out here, but we didn't get to Wittigs yet, so hold that thought. If I did this with a Grignard tends to give me an alcohol. So what if one step before this, I actually did have an alcohol, and in having an alcohol, I can figure out, that would be the new bond, I can figure out where and how a Grignard would have taken place. And notice the colors are new bond, new carbons being added. Now, can you try to envision a reaction that grows the chain so it looks this way? Why, yes, of course. We know that the alcohol could have come from a carbonyl, and that could have been my Grignard. Or it could have been the other way around, but why not? Let's do it this way. If this came from a carbonyl, what does that look like? My original two carbons coming off the chain with an aldehyde, and then the Grignard is simply an ethyl Grignard like that. That's step 1. Step 2 would be H+. Make sure it's step 2, because if it's step 1, you destroyed your Grignard. So then all I have to do is turn my alkene into an aldehyde. This is a series of orgo-1, orgo-2 reactions, so let's see how much we remember. Turn the alkene into a terminal alcohol is probably your easiest, best bet. Not probably, it is your fastest reaction here. The terminal alcohol will be an anti-Markovnikov addition, which I then oxidize to an aldehyde, react with a Grignard, and somehow remove the water. I always like to start with my intermediates first, then go back and add the reagents. The first reaction is something you covered in Orgo 1. This would be BH3, THF, step 1. Step 2, NaOH, H2O2. I think earlier in the session I forgot THF, but it should have been there. Once I have my alcohol, I want to turn it only into an aldehyde. I don't want to go to the carboxylic acid, so that would be PCC. Remember, PCC is approved. It doesn't go all the way. The Grignard I already filled in because we were talking about it. And once I have the alcohol, I want to dehydrate. Oh, this is a tricky. I made this trickier than it has to be, because I could have gotten the pi bond going in both directions. Yeah, we're going to have to put plus side products. sometimes the professor will say no side products, but in this case, plus side products. And the reason for that is if we use H2SO4 for an elimination reaction, for a dehydration elimination, then we could have gotten that, but we could have also gotten the pi bond going this way. And that would not, that would give me a side product. Since the molecule is equally substituted on either side, we can't control for it. So I'm just going to put plus side products. If you didn't want side products, then I would go with a Wittig reaction, because then you control exactly where that final pi bond comes in. Speaking of the Wittig reaction, there is quite a few additional reactions that we haven't gotten to for this chapter. The more advanced reactions like the imine, the enamine, the Wittig, thioacetal, the Raney nickel reduction, and a couple more. So sessions like this that I do here on YouTube, these are meant to be an introduction, a beginner session to give you a good foundation for the starting material. But then for the even more advanced session where I go into detailed mechanisms, advanced reactions, lots of practice, solutions, and the solutions to any worksheet, the solutions to any quizzes that I have on my website, and the ability to review your worksheets with me and ask daily tutor questions. All of that is included in my membership site. And if this is not something you're familiar with yet, go ahead and take a look at leahforsci.com/join. So as a reminder, what's included in the study hall is everything you need for Organic Chemistry 1 and Organic Chemistry 2. I have a lot of videos on YouTube, but these are the beginner topics. The study hall videos are more advanced with step-by-step breakdown of the mechanisms, the products, and lots of more advanced practice, as well as working with me. So I have a tutoring group where you can post your questions every day. Questions on anything you didn't understand, questions on whatever you're learning in lecture. If I do a worksheet for a session, like a lot of these sessions, I do a worksheet, you can post questions on those as well, so that it's not only getting the answer, because a lot of times you have a book with an answer key, but rather I didn't understand this, or how to get to this, or how to solve it. So if you want to learn how to do the questions that you're stuck on, you want to learn the what and why behind something you're not comfortable with, that's where the study hall comes in. So the link is leahforsci.com/join. And any questions that you have on anything we discussed today, make sure you leave it in the comments. With that, have a wonderful evening. Don't forget to go to leahforsci.com/orgolive for the notes from tonight's session. Take care, guys, and have a great evening.